Hey guys, so now I'm going to go over Unit 5, Lesson 5. I think this is the last lesson, and so way to go. You're almost done with Unit 5. There are a few more laws here, and so I'm going to go through all of the math problems from this lesson so that you're ready for the quiz and you're ready for the test and you get the answers right on the actual lesson. So there are four main laws that they introduced here. The first law is the combined gas law, which is this equation here. The second is the ideal gas law, which is this equation here. And I want to talk about the differences here. Both of them have P and V and T in them, P, V, and T. But you'll notice that the combined gas law has it like a starting P1 and then a P2, and then a V1 and then a V2. So we know to use this equation if we are given a scenario where the pressure and the volume and the temperature are changing to a new one. We know to use the ideal gas law if they are not changing. They give us a few variables and they ask us to solve for the pressure or solve for the volume. R in this equation right here is a certain constant. It is always this number right here. And then N stands for moles, which is kind of weird, but then N for like the number of moles. That's what N stands for. Dalton's law of partial pressure, which is actually kind of easy. It just means that if you have a total pressure, the total pressure comes from adding up all of the individual pressures within something. So if you have like a balloon of helium and nitrogen, the total pressure is the sum of both of the pressures of helium and nitrogen. And then Graham's law of diffusion tells you like how quickly something diffuses out, or the rate of diffusion. And M stands for molar mass. And so we will look at all of these when we do these today. Start with problem number 3. Grab a piece of paper and we'll go through it together. It says a sample of air with a volume. Hold on, let me zoom out a little bit. There we go. A sample of air with a volume of 25 mil. I'm going to go ahead and write that down. My V equals 25.0 mil. A pressure of 100 kPa. And a temperature of 22 degrees C. Let's go ahead and add 273 to that so that we don't forget, because remember, it needs to be in Kelvin. Your degrees Celsius always needs to be converted over to Kelvin, and the way you do that is by adding 273 to it. So this is 295 Kelvin, which is what we want. That's the unit we want. And that is compressed to 11.5 mils. Mils is a unit for what? Milliliters is a unit for volume. So it looks like I got a new volume. It got shrunk up and compressed. We crumpled it up, okay, to 11.5 mils with a pressure of 225 kPa. What is its new Celsius temperature? So it wants the temperature. And when we solve for it, we're going to solve for it in units of Kelvin. And then we can convert it back to Celsius. It wants it in Celsius. So what equation do we want to use? Well, we have a starting pressure, volume, and temperature, and then we have an ending pressure, volume, and temperature. We can see all these changes in these units. You see these double units, okay? So that means that we're going to want to use the combined gas law equation. So I'm going to write that down. P1 V1 over T1 equals P2 V2 over T2. And we're going to plug in and solve for X, which is our T2. So my P1 is 100. I'm going to remove the units just to like be less confusing. My V1 is 25.0 milliliters. My T1 is 295 Kelvin. So P1 V1 over T1 equals P2, which is 225, times V2 divided by T2, which is my X. So I need to get X by itself, and it is on the bottom. There are multiple ways that you can simplify this and solve for X. What I would do, it's just me, I would go ahead and punch all the numbers in. I kind of want to simplify it. Like I'm going to go ahead and simplify this side. So 100 times 25 divided by 295 is 8.4. So I'm going to just rewrite it over here that the left-hand side equals 8.4. All of this does. And then on the right, it's 225 times 11.5 on top, which is 2587.5, divided by my x. I still need to get x by itself, and it is on the denominator. So when x is on the denominator, we have to get it out of the denominator first. We have to get x in the numerator. So I'm going to multiply both sides by x, because when I do that, my x will cancel out on this side like this. And now I'm going to rewrite it that 8.4 times x equals 2587.5. So now I need to get x by itself. It's in the numerator, which is great. And I need to get that 8.4 to go away. So I'm going to divide both sides by 8.4. And I have my answer. I'm getting 308 as my answer. And remember, that's in units of Kelvin, right? And they want it to be in units of Celsius. So we need to subtract 273 from that. 308 minus 273. And I get 35 degrees Celsius as my answer for number 3. Okay. Number 4, a weather balloon with a volume of 50.4. So I'm going to write that down. My volume is 50.4 was launched from a ship in the Indian Ocean where the temperature, my T, is 30 degrees C. Let's go ahead and convert that to Kelvin. So 30 plus 273 is 303 Kelvin. And the pressure was 100 kPa. At an altitude of 9,000 meters, that's not really important. The height doesn't matter. The temperature dropped. So now the temperature dropped. Now we have a T2. The temperature dropped to negative 48 degrees C. Let's add 273 to that. So we need to do negative 48 plus 273, which is 225 Kelvin. And the atmospheric pressure has dropped to 30.8 kPa. So I have a P1 and a P2, a T1 and a T2. And it says, what is the volume of the balloon at that altitude? So that's my X. So again, it's the same setup. I'm going to use the ideal gas law. The combined gas law. And plug everything in. Okay. My P1 is 100. My V1 is 50.4. My T1 is 303. And that equals P2, which is 30.8, times X, my V2, divided by my T2, which is 225. So I need to solve for X and get X by itself. You can do this multiple ways. I'm going to go ahead and simplify it and multiply everything on the left. So I'm going to do 100 times 50.4 divided by 303. And I get 16.63. That's everything multiplied and divided on the left. And then over here, I'm going to go ahead and simplify this. I'm going to do 30.8 divided by 225 to go ahead and simplify that. Like this is divided by that, right? So 0.137x. Okay, so see, I just simplified my numbers. I need to get x by itself. So I need to divide by 0.137. So I'm going to do 16.63 divided by 16.63 divided by 0.137. And I am getting, for my x, 121.4 liters. It's not a negative. I'm just saying that is what it is. This is problem number 4. Let me double check that that was an answer there. 121.4. Theirs rounded to 122. So sometimes there's a little bit of a rounding difference. And so 122 is going to be the correct answer there. Okay. Number 14, an average incandescent light bulb with a volume of 0.0130. So we need to go ahead and write this down. My volume is 0.130. It contains, this is like a mass, 0.216 grams of argon gas. After the bulb has been burning for a few minutes, the temperature of the gas reached 100 degrees C. What was the pressure of the gas at that temperature? Hint, first find the number of moles. So nothing changed. It was not like we have a V1 and a V2, a P1 and a P2. And so when we have pressure, volume, and temperature, but we don't have like any change, we're going to use the ideal gas law. So I'm just going to write it down and see if we can kind of plug it in. It's P times V equals N times R times T. And R is always 0.0821. And the units are liters, atmospheres, moles, and Kelvin. And those units are really weird, but it tells us, okay, my temperature units need to be in Kelvin. Let's go ahead and add 273 to that. Okay. My volume is already in liters, so that's good. And my mass needs to be in moles. So for AR, let's see. What's confusing here for argon gas, we need to convert that to moles. We have grams of it right now. We have 0.216 grams of AR. It doesn't specify it here, but argon gas is going to be doubled. And I think that's kind of a mistake built into the lesson. They should have told you that argon gas is AR2 rather than just regular AR. So I'm telling you, argon gas is AR2, and we need to convert that to moles. So you can look up online what is the molar mass, or just look it up on your periodic table, because it's just the number beneath it, and then we multiply it times 2. So the molar mass of 1 AR is 39. Actually, never mind. Okay, I'm going to rewind here. Okay, so we have 0.216 grams of AR, and we need to convert that over to moles of AR, because this N is always going to be in units of moles. So if they give you grams, you got to convert it to moles. So we're going to write down what we start with. We're going to multiply, and we want to get to moles, and we want grams to cancel out. So grams is going to go on bottom. And so we need to look up the molar mass. We need to look up how many grams are in a mole. We can just use our periodic table for that. It's just the number beneath argon. Oh, shoot. Okay, we're going to restart again. Okay, so what do we do from here? Right now we have our pressure, our volume, our R, and our temperature. Our pressure is our X, right? So our N needs to be in units of moles. And right now we have it in grams. And so you need to take the gram amount that they give you and convert it over to moles. So you always write down what you start with, multiply, put the unit you want to get to on top, and the unit you want to cancel out on bottom. So how do we fill this in? How many grams are in a mole of AR? Well, you can just find that on your periodic table. It's just the number beneath AR on the periodic table. Or you can look it up like this, molar mass of AR, and you're going to get 39.948. So I'm just going to write that down. That 1 mole of AR equals 39.948 grams. So where should the 1 go and where should the 39 go? Well, 1 mole of AR. So the 1 goes with the mole, and the 39.948 goes with the gram. Okay. So we need to do 0.216 times 1, which is just 0.216, divided by 39.948. And I am getting, when I do that, 0.0054 moles of AR. Okay, so that is my moles of AR. So now I can plug everything in. I'm going to kind of squeeze it right here. My pressure is my X, so I'll do that as red. So P is right there. My volume is 0.130. My N is 0.0054. My R is 0.0821. And my T is 373. Okay. So now I'm going to simplify it by multiplying everything on the right. So 0.0054 times 0.0821 times 373. Okay. And I'm going to rewrite it right here. I'm going to make a new slide. Okay. So we know that X times, what was it? 0.130. I'm just rewriting that. And then I multiplied everything on the right, and I got 0.1656 when I round that off. So I need to get x by itself. We're going to divide both sides by 0.130 so that it cancels out. So that divided by 0.130, my x, which is my pressure, is 1.27. I think that rounds a little bit differently here. Let's see. The problem has it rounded a little bit differently on here. This is interesting. They solved for it the problem solved for it a slightly different way, and so their number got rounded a little bit differently. Their pressure was 1.37 that they calculated as the right answer. We got 1.27. They solved for it in a slightly different way, although this way you're great to go for it and do this way. So the pressure is 1.37 atm. Okay. For problem number 17, a scuba diver uses a tank of compressed mixture of oxygen and nitrogen. Which gas effused more quickly, and what is the rate of effusion of nitrogen compared to oxygen? So nitrogen is our R1 and oxygen is our R2. So I'm going to write that down. Oxygen and nitrogen, when they're by themselves, they are diatomic. There are 7 elements that are diatomic, meaning there are 2 of them. They combine together when they're by themselves. And these are these are part of those 7. So N2 is our R1 and O2 is our R2. And then we need to figure out, and plug it in here. We need to figure out the M2 and the M1. That's just their molar mass, which you can find beneath each element on the periodic table. So the molar mass of nitrogen, if you look on the periodic table here, it's kind of not zoomed in very well, but the molar mass of nitrogen okay. All right, so when we look at our periodic table, the molar mass of nitrogen is 14. The molar mass of oxygen is 16, okay? So 14 times 2, because there are 2 nitrogens, so 28. And then 16 times 2, which would be 32. And we're going to plug those in. So R1, which we don't know, over R2 equals the square root of M2, which is the 32. So see how it says M2? Well, it said that oxygen was our R2. So the M2 is going to correlate to the oxygen, and the M1 is going to correlate to the nitrogen. So we need to do the square root of 32 divided by 28, which you can just do an online calculator. The square root of 32 divided by 28. And I get 1.069. Okay, so this is equal to 1.069. So we don't know R1 or R2, but we know that overall that divided by that is 1.069. And our R1 was nitrogen, right? It was nitrogen. So that means that nitrogen diffuses 1.06, or we can say 1.1 times faster. Okay, so you just kind of divide the molar masses, take the square root, and that tells you how many times faster the R1 goes compared to the R2. And it tells you which one is R1 and which one is R2. The last problem, a researcher near Antarctica was conducting an experiment that involved a collection of carbon dioxide gas by water displacement. Okay, it was a little chilly in the lab at the time of the collection. It was 16 degrees Celsius. Allowing for the vapor pressure of water, what was the pressure of the CO2 collected? Something that they don't tell you in here that's kind of annoying is that you're going to assume that the total pressure is 100 kPa. They should have explained that in the problem, but they did not tell you that. The total pressure is 100 kPa. You have CO2 and H2O, and those are going to add up to the total pressure of 100 kPa. Okay? It's asking us to find the pressure of the CO2. So we need to figure out the pressure of the water. They gave us the temperature, and if we use a certain table in our chemistry reference guide, it's table B-6, we can convert that over. So the temperature was 16 degrees, which correlates to a vapor pressure of 1.8. 1.8, okay? And so you can literally just look at table B6 to convert temperature over to, did I say 1.8? To convert temperature over to pressure. So that is the pressure of the water. So we know that CO2 plus 1.8 equals 100. So how do we find CO2? Well, this was being added. And so to get CO2 by itself, we can subtract 1.8 from both sides. So 100 minus 1.8 is 98.2, which hopefully is an option on there for number 19. Yep, just 98. They rounded off to 98. So that is the pressure for CO2. If you have any other questions regarding this, please come to my classroom with your notes that you took, and I'll be happy to help you out.